questions at all? All right, let me just tell you what we're doing now. Okay, we're going to be talking about antennas. Now, I could bring down a bunch of different antennas, but I think most people know the simplest antenna you can think about is just a straight wire. It used to be called an aerial for an antenna on a car. You remember still those things? That just a straight wire. That's all you need. And usually what happens is they drive a current through that wire, and the current will cause an electromagnetic wave to be launched. I'm just leveling with you. That's the simplest ones, but they're complex in size. The one you see more of today than anything are dish antennas, parabolic dish. They're on top of roofs everywhere. If you have, believe it or not, we have direct TV streaming that we get through the actual cable, or I think it's WOW, it's a service, it's a cable service here. But we have a dish on our roof from the last owner of the house that we could probably use to get, a lot more channels. We may do that. That's the parabolic dishes everywhere. Matter of fact, when I was on the Eisenhower, the legacy radars, that means things that are left over from long ago, the legacy radars were parabolic dishes that just rotate. And they're still used today because they're very effective. But so parabolic dish, does everybody understand what I'm talking about? But when I say parabolic dish antenna, it's basically a soup bowl with a radiating element in the center that's blast side. And they're reflector, think of a reflector telescope, that's basically the same thing. Antennas can also just be a whole lot of little slots that are that are driven across it, but I'll show you a bunch of different types of antennas. And they're used for one purpose primarily, to radiate or to listen to a signal. That's the primary thing that's done, antennas do for us. So the way we start this thing, and the best way to do it, and try to appreciate one thing. If some of this stuff seems a little, why are we doing this? It'll come together. But what we end up doing is we say we have a little chunk of current. It's going to be short. It's going to be of length L, and L is going to be much less than a wavelength. And then on this, we'll have a current I. Just call it I now. And we're going to say we're going to come out some radial distance R away, and there'll be an angle theta. We might as well call this the z-axis. Okay. So we got a little chunk of current here. All right. And now it's going to be radiating upward, or the current's motion is vertically that way. And now we're going to talk about a vector magnetic potential here, A. Now, I'm going to just put these things down here for now. First, before I actually write the mathematical equation for A, the curl of B is equal, the curl of A, is equal to B. And since B is equal to mu H, you could say H is equal to the curl of A over mu naught. And this is in free space. By the way, what we're talking, well, let's do this way and check. Then, when we take a look at the next equation, we know curl of H is equal to typically J, but J is going to be assumed 0. We're going to assume that we are in free space now. Curl of H is J omega mu, or J omega epsilon, epsilon times E. Or we can say E is equal to 1 over J omega epsilon times the curl of H, which means it's 1 over J omega epsilon. And then the curl of H is the curl of A, so it's really the curl of A divided by mu. So you got epsilon out, mu naught there. I'm not trying to just do a bunch of mathematics for no reason. You have to at least understand, if we have A, we can get B. Well, we can get H. If we have A, we can get H, and if we can get H, we can get E, according to these vector identities. Now over here, E, I'm just going to complete this. E here is really equal to 1 over J omega mu epsilon, And then this becomes the gradient divergence of A minus del squared of A. I'm gonna stop there with the math on that for now. I'm gonna go over here and I'm gonna say what A is now in terms of this current. So A here, we're assuming L is small. Matter of fact, we might as well do it this way. You might as well call this a differential DL and call this a differential dA. This is equal to mu over 4 pi. Then it's divided by the magnitude of R. Then it's times I, and then DL here. It's gonna have a vector sense. So it's gonna have not only a dimension of length like DZ, but it's gonna have a vector sense, which would be AZ. Y'all follow me? So it's gonna have magnitude and direction. Then it's gonna be times e to the minus j beta R. And that is the differential magnetic vector potential. And the total magnetic vector potential A would be equal to mu, it's really almost always mu 0 over 4 pi. Then it would be the integral of I dl, and it's e to the minus j beta R over the magnitude of R. And this would be over the length. So it would go from typically minus L over 2 to L over 2. And that's the magnetic vector potential. Now, let me just tell you from, if I was sitting where you were, this is what I would want to hear at this point. Here's the real deal with this. This magnetic vector potential is like the voltage potential. Now, think for a moment back in the day when we were talking about solving electrostatic problems. Do y'all remember how if we had some charge configuration here, some rho that's a function of X, Y, and Z, and we had some, basically a charge, some blob of charge, doesn't matter how it's configured. If we went out a distance R, we could say that we could get V out here by integrating, and it would be rho as a function of, say, X, Y, and Z, right? And it would be over 4 pi R, where R would be the distance vector between here and here, over the volume that this existed over, right? And this was a scalar. Do y'all remember that? The voltage is a scalar. And if you wanted the electric field from that, you could say the electric field was just equal to minus the gradient of the voltage. Does everybody recall that? Now, getting a mathematical equation for V most of the time is much, much easier than writing the mathematical equation for E for all the components. You have to get EX, EY, and EZ, or have to get E rho, EZ, and E phi. You remember that? So this one is easier to do, and then this gradient operation is much easier to do. The number of mathematical steps is greatly reduced. In the same way, because A has really only one vector. Well, I mean, if I is directed vertically upward, then A is vertically upward. It's like a scalar, even though it has a vector sense. It's only got one component. Y'all follow me? Then these operations, the curl of A, it's just like the gradient operation. It's easier to do. That's the only reason we do this. All right. Now, something else that in his book he'll talk a little bit about. If you have a vector, and this is A, and if both the curl and the divergence of the vector are given, then it's uniquely identified. Does anybody remember this from your math classes? All right, well, it means if both the curl and the divergence of the vector are given, it's unique. So what happens over here, you see how you have a divergence of A? We can uniquely identify that in a way that suits our purposes and makes it easier to solve for the actual value of A. And this is called a gauge condition. Have you ever heard of condition, like gauge condition at all? All right, a gauge condition is something you're going to learn about, but allows us to select a divergence of A value that makes the solution very easy to attain. All right, now this is a little bit beyond the scope of what Wentworth's book covers and probably what we should cover in this class, but I wanted to give you a peek at one thing. Let me do it here. So, if I have curl of H equal to J plus J omega epsilon E. Now, you don't need to write this down. I just want to at least give you a peek into some of this stuff. Now I go ahead and I said, well, that's curl of A, right, over mu 0 is equal to J plus J omega epsilon E. Y'all follow me on this? Now I come down here and I didn't put this down here, but I'm going to see what the book has what I'm about to do. I don't think it does, but it might. Okay. This isn't in this book, but the E field, remember for electrostatics, the E field is minus the gradient of the voltage. Do y'all recall that? E is minus the gradient of the voltage. And when you have a time varying phenomena that causes electromagnetic propagation, you have to add on minus J omega A. Now, I'm going to do this. You don't need to write this down, but I'm going to at least let you see this. So if I multiply both sides by mu naught here, you get this. This is a very classic equation, by the way. Now, the next thing I'm going to do is just break this up into the vector identity, and that's the gradient of the divergence of A minus del squared of A is equal to mu 0 J plus J omega mu epsilon, and then it's going to be minus the gradient of V minus J omega times A. Just bear with me on this one. You'll see what I'm doing with this one. So now I've written everything in terms of both J and A. J will be a source current. It would be this current right here. Y'all follow me? There is no J in free space, so this is going to be a source current. They come down here, and what they end up doing is this. They're going to take this term right here, now it's separable, and this term, and this term, and they're going to make them the same. And what it boils down to, here's what's going to happen. You're going to have divergence of J, or divergence of A, right here, and it's going to be plus J omega mu times epsilon times V will be equal to 0. Now, here's what I'm trying to show you. You see this gradient operator here? All right. Inside the gradient operator is divergence of A, right? I'm going to set that equal to this delta V term. That's called the gauge condition. And when I do that, and I plug it in there, then I get a second equation. I get del squared of A, when this comes to this side. I get del squared of A plus omega squared mu epsilon times A equals minus mu J. All right, now this is y'all see how, if I go ahead and I use this right here, I can put divergence of A is equal to minus j omega epsilon V on this side, and then hit the gradient operator. It will cancel this term and this term. Just go with me on this one, all right? What's left is this, all right? This is called using the gauge condition. Now that equation right there is the Helmholtz equation. It's a second order equation. But remember, A here, when you solve it, will only have a component in the j direction. It's not going to have, in general, 3 components. That's the idea. So, we went to the whole solution. This will probably take a class period and a half. This is something that at least you should see for one time, hear about it one time, because later on in your coursework, if you go probably at the, if you take the antennas course, or if you take any of the senior electives that have to do with electromagnetic field propagation, they'll start with that gauge condition and derive a lot of stuff. But Wentworth's book doesn't do that. He does say that this is true, and this is true, and then he comes down to this. After all this is said and done, I like to say this here, and you know, I'm sitting where you're thinking about where you're sitting. Unless you see it applied to something, it doesn't mean a whole lot. I got to tell you this, at least being aware of it is going to be important. This is, and you can look at us up and learn more about it, but the gauge conditions allows us to solve so many things. Okay, back to this thing right now. So that's just generally true, and then once we have A, we can get H, and then we can get E. With me on this? Now I'm going to keep going on this. Now I'm going to go back to the problem. Let me start from scratch here. So now I'm going to say, redraw that. Now I have a short diagram. Right here. Dipole has a length dl, or I'm going to call this L. L and this L, and L is going to be much less, there's less than, much less than lambda. It's a short dipole. This is called a short, write this down, or Hertzian dipole. And I'm going to come out, call this the z-axis. I'm going to come out some angle, theta, and I'm going to get A. So now I can just write this down because this is assuming the length of this is short, and there'll be an assumed current I naught on it in this direction. That's the length. A will just be equal to mu0 over 4 pi divided by R times I naught AZ, and it's going to be DZ, and then it's going to be times the length, well, not DZ, but L, pardon me, L. Let me do it this way. I naught times L magnitude in the AZ direction. Then it's times e to the minus j beta r. At that point, I have A. Now, the reason I didn't need to do an integral is because I'm saying the length of this is so short that effectively nothing varies inside the integration. So you just, when you integrate dl, you just get L. Y'all follow me on this? There's no significant value changes. Now I get down to this point, and in Wentworth's book, he's going to say, what we're going to do is make AZ, we're going to go to cylindrical or spherical coordinates. AZ itself is going to be cosine of theta AR minus the sine of theta A theta, And this is just a standard transform to go from Cartesian or cylindrical system to spherical. And here's the real deal. If this is the AZ, it's a unit vector in the AZ direction. All right. And this is the angle phi. Then the component in the AR direction would just be cosine of phi, if you follow me on that, right? Because this has got a unit vector length. This would be a cosine phi times 1. You all with me? Can you all see that? If that's a right triangle. if this is electron, right there. And this is actually a vector that's going in this direction. I mean, the A phi direction is this way. So this length is actually minus sine theta A phi, and that's the unit vector business. So then when it comes down here, it's going to say A is equal to mu 0 over 4 pi I naught times L over R, and then we put in cosine of phi A R, or R, minus sine of phi sine of theta, pardon, A theta, and then it's times e to the minus j theta R. And now, at this point, I'll tell you where this is in his book, so you can follow. And his book does this a little goof. It's not that smooth as I'd like to see it. So on page 442, if you have your book, then at that point you do the curl of A. So now I know that the curl of A, maybe I should go here, do it over here. Curl of A is equal, divided by mu naught, is equal to H. When we take the curl of A, I have to take the curl of all this, but what I can do is take the constants out in front. I have mu naught I naught L over 4 pi. And then I have to take the curl of cosine of theta AR minus sine theta A theta, and this is times e to the minus j beta R. So it's the curl of this. Now, in your book, if you go to the back, and you will see the curl defined for spherical coordinates. Now, you can take a look at, you have your books with you guys. If you don't, right back here, the curl is defined. Well, actually, it may take a little time to do this one. But at the end of the day, when you do the curl, you're gonna, in the way Wentworth does it and structures it here, I'll show you what's important in a second. You get this. After the curl operation, you end up getting, it's equal to, yeah, he does it, I naught L over 4 pi, takes all that out in front. And then he has this term, e to the minus j beta R over R. And then he's going to have, and I understand why he's doing it this way, j beta plus 1 over R times the sine of theta A phi. I'm going to explain something. I wrote it the way it appears in this book, and this is equation 845, and then you'll modify that somewhat in 846, but I want to just talk about this. When you do the curl, and it takes a little time to do this. Remember, I'm using a capital R. I should be consistent here. Instead of a small r, just because my small r's look like V's sometimes. But when you do this right here and get this, there's a couple of things to take note of. First, this varies a sine theta. All right. And that means something, that if you're right straight above, it's 0. You all see this because the angle theta would be 0, sine of 0 is 0, correct? So there's no H field straight above or straight below that thing, and that's important to note. Also, you can see that there's two terms. The first term really falls off as 1 over R. The second term falls off as 1 over R squared. All right, follow me on this. Now, here's the deal that happens. We're going to get the E field in a second too. The only term that we really care about, you're going to see this for far field propagation, the radiation field, is going to be this term. This term will go away, it becomes so small. Let me go ahead and tell you that after you do that, if I take the curl to get the E field, technically I would take curl of H divided by J omega epsilon to get the E field. Now, in his book for the E field, he doesn't even have that in there for the full E field, but that's okay. I think that's an exercise. He does show you the E field, and I'll put it down, but let me just say something about this right here. We'll get to this in a second. When you have this equation as such, and you look, and I said that I could factor out basically, I could factor out the beta the way he does in the next equation, but I'm going to show you something. Remember how I said we're worried about far field propagation? I gave you a speech some time ago about how there is near field energy around a capacitor and inductor. Do y'all remember that? And I said that that energy can be gotten back. Well, far field can't be gotten back. It's launched and gone forever. They're photons. They're not virtual. They're real photons. And the way we find out, you might say, the point where you're in the far field. If you've got that antenna, the question is, how far away do I have to go so that the near field energy is really no longer there? It's in the far field. What they do normally is they say this. They're going to take the magnitude of that and set it to the magnitude of this. So they say beta is equal to 1 over R. This defines the far field. Now, it's not a hard barrier. It's like up to there, it's all near field, and from there on, it's all far field. That's the point where all of a sudden, most of the energy and power will be radiant in the far field. So this is how we do it. So then I take 1 over this, and I get R is equal to 1 over beta. And I know beta is 2 pi over lambda. So then I say the point where the far field actually occurs, you might say, is lambda over 2 pi. And this is the point beyond which you are considered in the far field. And he has that in equation 8.48. Do y'all follow me on that, class? Now when you're in the far field, a couple things happen. And now I'm going to tell you what happens in the far field. I'll get to that in a second. And this is really the important part. So now, when you have your short dipole antenna vertically oriented, and it's got a length L, and L is much less than lambda, has a current I naught on it, constant current, by the way. And now, I'm at some distance R, and we're going to assume we're in the far field. So R is much, much greater than lambda over 2 pi. We're assuming we're in the far field. So this is far field. Then you're going to have an E field. Actually, you're going to have an E field, and you're going to have an H field. That are in the far field. And E field in the far field, I'm just going to call it E radiated. You can use anything that I identify. That's going to be J, omega, eta, beta. Or, I'm sorry, let me take it this way. J, eta, beta I times L over 4 pi R times e to the minus j beta R times the sine of theta in the a theta direction. That's the E field, the radiated component of the E field for a short dipole. The H field, if it's radiated, you can always get by just taking E radiated, dividing E radiated, and pick a magnitude of that. E radiated by eta. You know how the relationship for any plane wave propagated, you take the E field divided by 80, you get H, right? So basically you take that equation and just get rid of eta naught, and the vector direction becomes a phi too. So I'll write that down. This becomes simply J beta I times L over 4 pi R e to the minus j beta R sine of theta in the a phi direction. And it's important to understand these are the radiated components for E and H for vertically oriented dipole, short dipole. And this is sort of the traditional point where you start with antennas. Now, there's a couple of things you got to take note here. Looking at this. Just look at this one for a second. The E field. All right. If I take a look at this short dipole, it's got a current I there, and I take a look at a couple of things. If I was to graph using a polar plot the magnitude of the E field, just magnitude, you see how both of these are proportional sine theta, right? The sine of the angle. So directly above, there's nothing. And where does the sine become a maximum? Argument, 90 degrees, right? Sine of 90 degrees is 1. So what actually happens is if you were to plot the magnitude of the E field on a polar plot, you would see this. It would look something like this. This is where the maximum E field would be. This is the far field. Makes sense to everybody? Now here's the deal with that, why it's so important. It means when you have an antenna, a short dipole antenna, and you're going to see it's true for long dipoles too, that the maximum field radiation at a given R is always perpendicular to it. If the current's going this way, if you're at 90 degrees to that, that's where the peak E field, that's the direction for the peak E field radiating. So it's radiating a maximum in the equator, you might say. If you mount this thing on the Earth, if you're at the actual horizon, that's where the E field's a maximum. It's a minimum straight up or straight down. There is none. All right. It'll help you visualize what's going on. Next, after that, Dr. Wimper spoke this way. He talks about average power density that's radiated, which is important. And now, remember, we're talking about this in free space, lossless media. So I'm going to still maintain, we're assuming it's free space. So in free space, if you had a plane wave, how would you get, and you had the electric field, how do you get the power density? Remember that? Well, we could get the H field and could take 1/2 the real part of E cross H conjugate, right? You remember that? This is when the phasor domain. Or what else could we do? How about 1/2 magnitude of E squared over 2 eta? Do y'all remember that, class? All right, and I'll put it down here. In free space, the average power density, PF, is equal to 1/2 the real part of E cross H conjugated. I mean, we can do that. We can do that mathematically. What it will amount to is this. This will be 1/2 magnitude of the E field squared over eta naught, and it will be in the AR direction. There's an assumption here that this thing's located at the origin, right here. And we're trying to limit the amount of variation, so we can just cut to the chase about the theory and stuff. So when I take a look at this, this means the average power density, or it could be this way. You could say it's equal to 1/2 eta times magnitude of H squared, that would be far field H in the AR direction. Either one will get you. if you look at this, and we take the first one, 1/2, magnitude of the E field, well, this is the E field, right? Now look, the magnitude of the E field gets rid of this E to the minus J beta R. That's E at an angle. You all follow me? Magnitude, that's 1. So I have beta, put it down. I'm gonna have beta I L sine of theta over 4 pi r. All that's gotta be squared, and then I have to divide by 1 over eta in the AR direction. And I'm just taking literally the magnitude of the E field, and I stuck it in there, and I'm gonna square it next. So that means I get 1/2 beta squared, we'll simplify this, I squared, L squared, sine squared, over 4 pi squared, R squared, and divided by eta. With me so far? Here's where, depending on how you want to manipulate this, there's a bunch of things in the AR direction. In Wimper's book, he leaves it in terms of a lot of square values and sine squared. This is equation 8.51 if you want to write it down. But I'm going to tell you a few things that are nice to do. Because when I'm teaching EMC or electromagnetic compatibility and stuff, what I like to do is turn this into something that has to do with wavelength. So I know that beta, right, is equal to 2 pi over lambda. You all agree with me there? So what I can do is this. I can say this is equal to 1/2 times 2 pi over lambda squared. Then it's going to be times I squared times L squared sine squared theta over 4 pi squared. Then it's R squared, and you can make eta simply 125. I can leave it as eta naught though, eta naught, and the AR direction. Now I'm just modifying this, but I'm going to show you the reason I'm doing it this way. I know some of you are writing it. I'm not trying to get too far ahead. Once you're done, I want to show you something. Everybody's done with this. And again, I'm not trying to cause problems, but this is the way I do it. Can you all see there's a pi squared up on top and on the bottom, numerator and denominator? So I just erase that. That doesn't do much. So I get rid of that. Now, I've got 2 up top and I squared, that's 4, isn't it? And I got 4 squared down there. So what I do is get rid of this, put a 1 there, and then get rid of the squaring operator there. Go with me? Next thing I see is I have 2 times 4. I'm just going to modify it. You can write down the final form. 2 times 4 is 8, isn't it? So what I can do is just take 8 out in front. Then I have something else. You see how I have L squared there? Well, now if I put L over lambda in there, what this is a ratio of the length of the antenna to the wavelength. It's short, right? So this is going to be a small number. Y'all follow me? So I want L over lambda squared times 1/8 I squared over, or I squared times sine squared over R squared. Sometimes people will write the 120 pi, but we know that eta naught's 120 pi in free space, right? Now this one is a little easier to see manipulate than Wimper's equation. If you have, anybody have your book there? Take a look at what I've talked about. Look at this equation 8.51 and all those terms. You got a square and he's got a lot going on there, right? All right, it's easier this way, I think. For me it is. Now, a couple of things. At a given distance r, what is the maximum power density? So we're going to assume we're at a given distance r. Well, it will be when the sine is equal to 1, right? It will be at 90 degrees. So now we can say that the P max for a given r, P max, or P average power max actually, P av max is just going to be these terms, which are 1/8 times L over lambda squared, I squared over eta naught. And that's P max at R. And of course, this is the P max that would be at a given R. At R. And the next thing is that we can get, hope I'm not jumping too far ahead. Yeah, we can get the total power radiated too. Now look, if this is the actual, I'm gonna do something here. I'm gonna say this whole equation can be rendered as just P max, which is all that up there, it's the front end of this, divided by R squared times sine squared in the AR direction. Are you with me on this? I've replaced a lot of those terms just with P max, okay? All right. Now, I'm gonna come over here, I'm gonna get the total power radiated. It's getting interesting, I think. So how do you get total power radiated? This is a power density. I didn't put the units on this, but it's in watts per meter squared. So how do you get the total power radiated? This is the average power density. How do you think? If that's a density, what do we have to do? That's power, that's watts per meter squared. If we want the total power, which would be in watts, we have to what? Integrate that over the spherical surface that it exists on, right? At a given distance. So to get total power radiated, this is going to be P radiated, total power radiated. We simply go ahead and we integrate the power density, called P av, and that's a vector, and we're going to integrate it over the entire surface. This would be a closed integral. So what that boils down to, it's a double integral of the power density, and I'm going to use just that P max business over there. So it's going to be P max over R squared, and then it's times sine squared of theta, AR, dotted into, do you remember what the differential surface is in spherical coordinates at a given R? The outer surface. It's R squared, think about this, R squared times sine of theta, right? D theta times dt. And it would be in the AR direction. Do you remember that as a differential surface? Vaguely? Okay. Most people, unless you work with this a lot, you don't remember these things, because there's a lot, if you're doing differential calculus and stuff, and you're working a lot of problems, it stays with you for life after a certain point. But there's a threshold effect. You gotta do so many problems and all of a sudden, it's like F equals MA, you never forget it. D is I times R. Now I have to put the limits on. What's the limit for theta? Think about it. North pole, theta equals 0. South pole, theta equals 180 degrees of pi, right? So from 0 to pi for theta. What about phi? Phi is in the horizontal plane from 0 to 360, right? Or 2 pi. Do y'all remember that, guys? Right. When we go north pole to south pole, it's pi. That's theta. From you might say from east all the way back to east again, that's 2 pi. Now, one thing you can see before I do this integration, because it's not going to be hard to see. You see how the R squareds cancel on top and bottom, which is nice. And that also is, there's a point I'm gonna make. That means that if you have a given spherical surface R, that is where the actual radiating point's at the center, that the energy that's being radiated, or power being radiated, it is something that's spreading as 1 over R squared, but the total amount of power at any given point being radiated is a constant. That's one of the things you should see from this. All right, next thing I'm gonna do is take P max outside, and that's just that term. Then I take a look at this and you see that nothing inside here is a function of phi. By the way, 8R is 1, is it? So I'm going to get rid of that dot product. Now, P max comes out front. Nothing's a function of phi, so when phi is integrated, I get phi evaluated from 0 to 2 pi is just 2 pi, isn't it, class? Y'all agree with me? Now, I'm left with this. I have to do the integral from 0 to pi. Now I got sine cubed theta d theta. I remember how to do it because I've done it many, many times, and it gets to be one of these things you don't want to do it anymore. Do you remember how to do an integration like that? Anyone?
Don't you separate, pull out a sine, and then put the sine squared in terms of the
Actually, probably put sine squared and replace it by 1 minus cosine squared. All right, so I'm going to go ahead and say this can be rendered as 1 minus cosine squared theta times the sine of theta. That would be sine squared theta times sine theta. D theta, right? You're right. And then what's the next step after that? You don't have to do this. What I normally do is say let u equal what? Cosine theta. And therefore du equal minus sine theta. Do y'all remember? Times d theta, right? You remember this is just doing substitutions. So I come here, and I can say that this integration, P rad here, is going to be equal to, and I'm going to take 2 pi times P max, leave that alone. Now I'll break it up. The first part, it's just the integral of sine theta d theta from 0 to pi. We'll get to that in a second. And then the second part is minus the integral. And if you look at this, this is going to be minus cosine squared or minus u squared times du, which is, and the sine theta d theta will actually make that a minus, right? Here's what I'm saying. I got cosine squared times sine theta. Well, cosine squared is u squared. Sine theta d theta is minus du, right? Right. Follow me? So this is actually 1 plus du here. And then I have to replace the limits. Now theta is 0, u is 1, isn't it? See that? It's cosine of theta. Cosine of 0 is 1. So the lower limit becomes 1. The upper limit, pi, when cosine of pi is what? Minus 1, isn't it? Minus 1. Just think about it. Cosine waveform, peak, 90 degrees at 0. At 180, it's minus 1. So to minus 1, and I'm going to do that. So the P rad, there's a better way to do this, I'm sure, but this is suffice. P max is defined over there. All right, integral of sine theta minus cosine theta. Do you agree with that, class? So I have minus cosine theta evaluated from 0 to pi. We'll come back to that in a second. And then we integrate u squared du, which is, I just try to get people involved here. What? U cubed over 3, right? All right, so then I have plus u cubed over 3 from 1 to minus 1. By the way, the steps to complete this integration are critical. All right, it's just, I do it one time because this props up over and over again. And some people, even with symbolic integration, will mess this up. So just do it one time. Over here, this is gonna be 2 pi times P rad, or I mean times P max, pardon me, P max, which is over there. And then now we put the values in. Well, what I'm gonna do is just switch the limits and get rid of the negative sign, so make that 0. And make that pi. So the cosine of 0 is 1, right? Minus the cosine of pi. Well, the cosine of pi is -1, so it's minus and minus 1 or plus 1 or 2. Y'all with me on that? All right, next, what about this one? Well, you can do it any way you want, but if you take a look at this, probably flipping the limits, throwing the minus sign would be easier, but you don't have to. We can go ahead and say this is plus 1. Minus 1 cubed plus 1/3 times minus 1 cubed, right? Minus 1 cubed. Everybody agree with that? This gets a little irritating, but finally, if you take a careful look at that, minus 1 times minus 1 is 1, times minus 1 is minus 1. Minus 1 is minus 2. I feel like it should be on Math Jeopardy now. All right. Then, I'm not quite done. I'm gonna get a common denominator over here, so it would be 2 times 3 or 6/3, right? 6/3 minus 2/3 is 4/3. Y'all see what I'm doing? So I'm gonna replace this baloney with 4/3. Finally, I can see that means it's 8 pi over 3 times that p, which is over there. And you can put it down. You don't have to use that one, you can use Wentworth's. 1/8, but you can see why the 1/8 gets rid of some problems real quick. Times L over lambda squared times I squared, I naught squared over 8 And if you look here, now remember I just replaced P max with that, the 8's cancel. So I'm going to get rid of them. That means the total power radiated from a short dipole is given by that. And that's easier to see and remember, even though I wouldn't ask you to remember that one, then where is Wentworth's? Okay. Total power radiated. Well, he does break it down. That's 8.55. Let's see how close is this. Should be up here, that was my bad. Forgot it up there, and that means the 8 should be up here. Correct that. Now, I'm just gonna tell you, we're gonna get it down to one simple thing as a function of I and M. So when I go ahead and I plug in 8 and naught, here I have pi over 3. 8 and naught is 120 pi. Then I have I naught squared L over lambda squared. And here, you can see I got 120, I'll let you copy that down, but the only thing I've done here, I'm sorry, but back in there, I forgot the 8 in there, was my bad. And when I square that and divide by 8, you're left with an 8 upstairs. If you come down to this point, and then you should be able to see 120 by 3 is 40, 40 pi squared. times that. And this is the power radiated. Let me go ahead and just write that. This is the total power radiated. And whenever I put a star on something, it means it's an important equation. You should have a grasp of the meaning of it, and we'll be using it. So that's total power radiated from a short dipole. I know there was a lot of math to get there, but I hope you appreciate it. Just remember, this is what it comes down to. And you can always get it, if you can get the E or H field, you can always get the total power radiated. And you can always, in the far field. And from there on, everything else sort of comes out of it. Now, next, I have to show you this. When we have this antenna, really, let me just show you a real diagram. Normally, you'd have some voltage source here, some plus to minus Vs, and it would be driving the base of this short dipole, right at the center of it. So I have this short dipole here of length L, with a current I naught in the vertical direction. And it's radiating power, right? That's power that's radiated, never coming back. It's not localized energy that collapses back onto it, like around an inductor or capacitor. Well, because it radiates power, the way we model this is we say that the antenna itself can be approximated by a radiation resistance. And so the antenna will look like some resistor, R, and they call it R rad, and this is actually pretty legit. There's a current I naught going into R rad. Now this is a standard type of thing you see in circuits. Remember, this is a time varying field, we're in the phasor domain. So the power radiated from a resistor, or power dissipated by a resistor, would be 1/2 times I naught squared times R, and this would be R rad. You all follow me? Now this is called radiation resistance. And since the total power radiated was 40 pi squared times L over lambda squared, right there, times I naught squared. I'm going to go ahead and just modify a few things there, but I've equated the total power radiated by the antenna to the power that would be dissipated by a resistor. The resistor was dissipating all that power. And then you can see the I naughts cancel, and you multiply by 2 and you get the radiation resistance. Which is called R rad, is equal to 80 pi squared times L over lambda squared. And this is an important one right here. That's the radiation resistance of a short dipole. Y'all with me? We'll do problems on this, but most of it's just plug and chugging the formulas once you've got them. But you have to understand radiation resistance is important. Understanding the radiated electric field and magnetic field is important, all right? Knowing how to get the power density is important. And now, after that, what I'm going to talk about is something. How many did the reading that I asked you? At least you're honest. It helps me know who I'm talking to, because when I just assume you did it and start talking, it's like talking to the wall. Yeah, right. So next, what I'm going to do is ahead and talk about what I call figure of merit. Now, if you have anything, you want to know how good or bad it is, and there's ways we can do that. Figure of merit is something that just gives an engineer an idea how good or bad something is, the goodness of it. So with antennas, this is my short dipole. What I want to know is how much better it can focus power than an isotropic radiator can focus. Here's what I mean. If I have an antenna, just a short antenna, and an antenna, matter of fact, doesn't matter what it looks like. And it's radiating some total power P rad, okay? For an isotropic radiator, at any given distance R away over the spherical surface, at any given distance R, the average power density would just be the power radiated by 4 pi r squared in the AR direction. Because that would be an isotropic. There's no variation of angle, either theta or phi. Y'all with me? What's a good example of an isotropic radiator? Anything. I mean, something that approximates it. Where it doesn't matter what direction, the same amount of power is going. Some power density at any given distance off. How about the sun? All right, if you think of the sun, think about electromagnetic energy being propagated. Huge spectrum, wide spectrum, right? But it doesn't matter as far as angle around from the sun where you are. It's about the same, the density of the radiated power. Now there is some difference with the actual, call it solar wind, but I'm not going to get into that. But just trust me, the sun is a pretty good thing, or a star. Think about it. So what we do is we measure how much better our antenna focuses power than an isotropic radiator. So the definition we talk about is, when we talk about directivity, that's really the average power density, or Pab, by our antenna as a function of phi and theta over the power average that would be for an isotropic radiator radiating the same amount. So if you think about it, it's going to give us a value that should be greater than 1 at some point. It should be a lot greater than 1. Do you all follow me on that? And I'm just saying this in a way to give you an idea of why we do stuff. So now I got my short dipole, got a current I naught, and I know what Pab is out, the average power density is as a function of angle and R. So to go about getting this is probably the easiest way to see it. We talk about the directivity D, and we say it's equal to 4 pi over something called a solid angle. Now, normally what I do when I'm doing directivity, and what probably should be done is, and I'll show you what this omega P is called, a solid angle. And the solid angle is equal to really the integral of the normalized power density. So it's Pab and it's normalized. I think he just calls it Pn in this book, but it's the average power density, but it's normalized. And that's a function of theta and phi. And it will not be a function of R. It's that integrated over the surface, and the surface of a sphere of radius 1, which the differential surface area would be sine theta d theta d phi. Theta would go from 0 to pi, and phi is 0 to 2 pi. Now, I'm gonna do some examples of this. Don't let this bother you. All right. But where this really comes from is if you take directivity in the fundamental definition, well, the average power density, if you think about it, I mean, I'm trying to say this in a way. Normally what you would end up doing is downstairs would be P rad, total power radiated over 4 pi r squared. That would be the average power density for an isotropic radiator. Up top, now you're gonna have to find the power density of your actual system. And remember, I wrote something over there some time ago, and I had, I'll just call it P max here. P max times the sine squared of theta. And this P max had a bunch of terms in it. Well, when you actually go about doing this, you're gonna see P max is gonna have an R squared in it too, and the R squareds will cancel. The 4 pi will come up top, and then P max can be written in terms of P rad. And ultimately, what happens is, this equation, I shouldn't have put a sine squared, I should just put an average functional form, just some f of theta, because we don't know generally what the actual form is. But when you go ahead and reverse engineer this thing, so you get it down to its essence, you come up with this. Now let me just say one other thing. When I take a look at the average power density normalized, what I mean is that you take the power density at any given point in space, so it'd be P average of theta and phi, and then you divide it by P average's maximum value at that range. And you can put an R in there, but it'll cancel. So this, when I say normalized power density, I'm saying that the largest value you can have is 1. And I'm gonna do an example in a second, all right? Because some of this, I think, needs a little exploring. This is the definition of directivity, but actually I should say it's the maximum directivity. It's D max right here. This is important. And the solid angle is important too, but you're gonna have to see them used. And I'm gonna bring this back. All right, so we're gonna stick with the short dipole and we're gonna see this. All right, so for a short dipole, the average power density, remember it was some P max that I had on there, it won't matter about this time. And it's gonna be that over R squared times the sine of theta squared. And you can actually omit the R squared. So then, when I normalize the average power, I take this value, R squared, times sine squared, and I divide it by its maximum value. Well, its maximum value is that. So I'm dividing it by P max over R squared, and it's simply sine squared theta. Now you see what I've done is, basically I've said, I've divided out the largest possible value that P max could have at any given range. And it comes down to a sine squared. Do you agree with me there? That would be the normalized power density. I think in his book he just calls it Pn, and that's fine if you want. He'll save me writing some stuff. So now, I want to get directivity B max, and that's equal to 4 pi over omega p, and omega p is equal to the integral of the normalized power density, which is sine squared theta, times, and he calls it the differential solid angle, but it really, you can say it's the differential surface assuming R equals 1. And it's sine of theta times d theta d phi. Well, theta will go from 0 to pi, and phi will go from 0 to 2 pi. I've got to make a point here, and it's an important one. This is the surface of an entire sphere. Follow me? If the radiation only occurred in an upper hemisphere, it would go from 0 to pi over 2. In other words, if we had an antenna on the surface of the Earth, it can't radiate into the Earth, all right? It would actually, there would be reflections and stuff. This can be modified, but it's over the surface that the antenna radiates. Now, what do you see happening there? I know you've been going at it a while. Can you all see that's a sine cubed integration again? I got sine squared, right? Times sine, so that's sine cubed of theta. Now, we did that just a second ago. I spent some time, and I'm going to tell you how this always breaks down. When you have a sine cubed integration, the first, or the outer part, d phi. D phi integrated is phi evaluated from 0 to 2 pi is 2 pi. I guarantee you that's always true. The inner part, when you have sine cubed integrated from 0 to pi, will always be 4/3. We just proved that, I think, if you remember. So it's this times 4/3, which means this is 8 pi over 3. This is a solid angle. So when we have a short dipole, when we look at the maximum value of directivity, P max, and this would be for a short dipole, that's going to be equal to 4 pi over quantity 8 pi divided by 3. I'm just taking this value, plugging it into the definition I've showed you. And this is going to be what? 3 halves, or 1.5. And that is the maximum directivity. Now I'm just going to finish up here. Y'all with me on that? So why is it so important? Here's why. It says the directivity in any direction, total directivity, D is a function of theta and phi, will be equal to D max times the normalized power density. P normalized P and theta, theta and phi. Well, for a short dipole, it's 3 halves. And remember, for a short dipole, the normalized power density is sine squared of theta. Okay, so that's the directivity for any angle. So how does that help us with problems with antennas? Here's how. I mean, with it, say you got a short dipole radiating. We went through a whole long spiel to get to this point. Why are we doing it? I mean, that's always a fundamental question. Why are you doing what you're doing? I mean, what benefit is it? Here's the real benefit. So I have a short dipole antenna here. Just say it's a short dipole. And I got a source voltage. And it's driving the current I naught on that antenna. This is a short dipole of length L. Okay. Now I can say, listen to me now, that the actual power density, P average, at any given range and value of theta, so for all theta, phi, and r, can be given as, here's where you gotta listen, because this is important. It's not in this book. You take the isotropic radiated power density. So if I'm gonna go ahead and just say that I'm radiating P rad is equal to, I'm just gonna call it P rad. That's radiated power density, which would be equal to 1/2 times the radiation resistance times I naught squared. With me on that? If I got a short dipole, I know the radiation resistance. All right. I can figure out the power radiated if I know the current, okay? Now, what I do is take the isotropic power density, which is P rad, radiated power, over 4 pi r squared, and then I multiply by the directivity. Because remember, when we had the whole benefit of defining directivity is how much better it is, or worse, than a isotropic radiator. With me? So I not just multiply that by the directivity, and I multiply this by the directivity as a function of theta and phi. And that is the isotropic power, that is the power density anywhere. for any antenna, by the way. If you know the directivity of an antenna and you know how much total power is rated, you can find the actual power density, any range for any theta and phi. Specifically for a short dipole, the average power density would be equal to radiated power density. I'm going to leave it as just P rad here, over 4 pi r squared. And then it's simply times 3/2 sine squared of theta. And that's the power density in the AR direction, anywhere. And that's nice. So this is for a short dipole. This is the general form for any antenna of any length. If you know the directivity and the total power rating. I might add one thing. I have not included some of the inefficiencies of antennas. They do have a resistance, any wire has a small but measurable resistance. So we'll modify this to the actual term that's used in industry. It's called gain, but not today because I'm a minute over already. I'm trying to at least be attentive of your time. I don't want to stretch it. I got through what I wanted to do. I didn't have time to go through the actual directivity and development the way I like to, but this gives you the real essence of why we get directivity so important. We're going to be talking about some things called beam width. Like beam width is where between the beam width we find out where most of the power radiates. You'll see this. These are logical things to ask. We'll take a look at patterns for power pattern and cylindrical coordinates, the power plots. I'm going to give you some homework. Please do it for Wednesday, okay? Now, I'm not going to give you a quiz on Wednesday. I'm going to give it on Friday. All right, so don't worry about that. But please be here and do this homework this time, okay? You guys got questions about it? Did you understand what I was talking about? The math, I know, just very easy. But you have to go through that to get to the E field and H field. And I'll say one other thing too. When you were at, a lot of times things like gauge condition and all that, I didn't have a really intuitive feel for that. If you don't worry about it. But you need to be exposed to think about it, because over the course of time, in the next couple of semesters, you're going to hear that and see this in a lot of different ways, probably. And then things start clicking and you understand the reason why. And last thing I'll say about this, remember, in engineering, everything we do is based on the physical world's knowledge of the physical world, where we have measurements and we have the mathematics to describe physical processes. It can be either continuous, for anything but continuous things, derivatives and integrals, or discrete domain, we have summations and difference equations. But integral differential equations are the way the universe is described. And what we do is we know the description of the universe, our universe, and we use that to engineer things, to create things based on the physical limitations that are there. And that's the engineering in a nutshell, honestly. We make the world better because we understand how it works through the physical lines. Keep this in mind, that mathematics is probably the one thing that allows almost everything we do to take place. So don't wince that bad when you see differential equations.